Let's look at number 7. Let's kind of think through this. On number 7, we don't have a chunk of something raised to a power, so we don't want to let that be u. I've just told you that a lot of times now we're going to let u be the bottom. But if I let u be the bottom, which is x squared plus 1, what would du be? 2x dx. And I've still got an x squared plus an x plus a 1. That's not working out for me very well. All right. Whenever the degree of the top is greater than or equal to the degree of the bottom, unfortunately, we're going to have to use long division to rewrite this. Okay? This is why we taught you long division with polynomials in Algebra 2. When the degree of the top is greater than or equal to the degree of the bottom. Now, you're used to only using long division when the degree of the top is greater than the degree of the bottom to find a slant asymptote, but this is different. Anytime the degree of the top is greater than or equal to the degree of the bottom, we're going to use long division. Okay, the way that we're going to do this is that the top part goes under the division house. So the x squared plus x plus 1 goes under the little division hut, and the x squared plus 1 goes right there. What do you have to multiply x squared by to get x squared? 1. And I'm going to stick it all the way over here to the right because I like to keep anything with an x squared lined up in this first column and anything with an x lined up in the first column and all my constants lined up in the third column. All right, then what you do is you take 1 and you multiply it by the x squared plus 1, and you get x squared plus 1. Okay, and once again, I'm going to keep my x squareds lined up, my x's, and my 1's. What's the next step? Good. You have to go through and change all the signs or subtract everything. And when you do that, what are you left with? Just x, because the 1 minus 1 cancels. So that's your remainder. The remainder is important in calculus because this whole expression, x squared plus x plus 1 divided by x squared plus 1, is equivalent to 1 plus the remainder over the divisor. It's supposed to be a parenthesis. Okay, so I used long division, and I took the result of that long division, including the remainder, and now that's what I'm going to integrate. Okay, can you see where this might be going? Yes. What you could do is you can break it up into each two different parts. We could do the and distribute your dx. We could do the integral of 1 dx plus the integral of x over x squared plus 1 dx. What's the integral of 1 dx? X. Okay, this one. Let's try to not use u substitution here. The bottom is x squared plus 1. What's the derivative of the bottom? 2x. So if I can make the top into the derivative of the bottom, then I'm good to go. But if I stick a 2 inside, I'm going to have to stick a 1/2 outside. So that integral is going to be 1/2 natural log of what? Good. Plus c. Okay, someone made a comment about the absolute value. Hold off on that for just a second. If you needed to go through the u substitution, you could. But y'all see how this one was, we could kind of work through it without writing down the u's? Okay. All right, I purposely did not put absolute value here, and I'm right. It's because it's x squared plus a positive number. That argument just needs to be, the argument of natural log has to be positive. And x squared plus 1, no matter what x is always guaranteed to be positive. Okay, that's always everyone's first question is, would it be wrong? I don't think so at this point. A long time ago, it was like 10 or so years ago, there was a multiple choice question that was something like this, and one of the choices was this, and they actually put another choice as with the absolute values, Okay, 10 years ago, I think they were, in your words, trying to screw you over on things like that. But they seem to have moved away from that. So would they count off on a free response problem? Maybe, maybe not. It depends on how they want to arrange the points on it. But technically, it's redundant to put x squared plus 1. I mean, it's redundant to put the absolute values around it. But they could count off for not having the exact notation right. I mean, you would get most of the credit. I mean, I would try and pay attention to it and not do it. It is a little mean. Okay, number 8. What do you want to let u be? The natural log of x. Okay, let's try it. You got to let it be something. So if u is the natural log of x, what's du? 1 over x dx. Do I have that? You sure do. There's your 1 over x dx. So you're really just integrating 1 over u du, which is the natural log of absolute value of u plus c. And u is the natural log of x. Okay, the question was, do you have to put the absolute value of x within the natural log of x? No, because ln x was already part of the problem. So it's understood that x has to be positive. You do have to have the absolute values here because the graph of ln x looks like that and is positive and negative. So you do have to have the absolute values. Okay, number 9, tan x. This is going to open up a whole new way to integrate some of the trig functions that weren't specifically derivatives of the 6 trig functions. With integrating using natural log, we are always using fractions. So can I rewrite tan as a fraction? Absolutely. Which tan as a fraction is sine x over cosine x. And if I have a fraction, hopefully, and there's not some other obvious thing to let u be, I would let u be the bottom. And the derivative of cosine is negative sine. Good. Good catch on the negative. So if I stick a negative inside, I'll need a negative outside. And it's negative integral of 1 over u, and then my negative sine x, sorry, this was a dx. If sine x dx is my du. So negative natural log of absolute value of u plus c, negative natural log of the absolute value of cosine x plus c. Okay, so unfortunately, I've given you some more things to have to memorize. So the integrals of your 6 basic trig functions are right here. You already knew sine and cosine. Tangent and cotangent are pretty easy to derive if you forget them. And those are the ones that are going to be asked most frequently. So you can memorize them or you can derive them pretty easily just like I did. The integrals of secant and cosecant, I have not seen them come up on the AP exam in a really, really, really long time. I will probably lightly test you over it at some point. If I give you a pop quiz tomorrow, I won't make you know the integrals of all these trig functions yet. Okay? So the ones you really need to concentrate on are sine, cosine, tangent and cotangent. The integral of the square root of 1 plus tan squared. Okay, isn't that something else? Sophia and Tamar are on the same page. Our big daddy is sine squared plus cosine squared equals 1. There are two other Pythagorean theorems, or Pythagorean identities. There's only one Pythagorean theorem. I do not have the other two memorized, but I know how to derive them, and that is to divide the big daddy by sine squared. If I divide everything by sine squared, I have 1 plus cotangent squared equals cosecant squared. Y'all cool with that? And if I go back to the big daddy and divide everything by cosine squared, then I have tan squared plus 1 equals secant squared. You have it mixed up. 1 over sine is cosecant, and 1 over cosine is secant. Okay, so 1 plus tan squared is the same thing as secant squared. And the square root of secant squared is secant x. And, I know, see, it looked like it was going to be really hard. And the integral of secant x up here in this little box is the natural log of secant x plus tan x plus c. But I don't really need the plus c because this is really a definite integral. Bless you. It's like the square root of x squared is just x. All right, so now I just have to plug in a pi over 4 minus plug in a 0. The secant of pi over 4. Cosine of 45 would be 1 over root 2, so the secant of 45 would be root 2. Plus the tangent of 45, or pi over 4, is 1. Minus the natural log. The secant of 0 is going to be OIO sine cosine. Tangent 0. Oh, no, wait, pi over 4. Duh. Wait a minute. The secant of 0 would be the same thing as the cosine of 0 flipped, which is 1. Okay, sorry. I'm slow. And the tan of 0 is 0. So the second half is the natural log of 1, which is 0. So your answer is the natural log of root 2 plus 1. Now, do I need the absolute values? No. Root 2 plus 1 is a positive number. Yeah. If your argument is positive, you don't need the absolute values.